The spring with damping is special in that it doesn't act like a simple harmonic motion in that it will keep going forever. At some point, it will start slowing down based on an enveloping function that we multiply by the regular sine function in order to get the position over time of our spring. It's not simple because it does not follow the regular cosine of x or sinusoidal pattern. So today we're going to be looking at a spring on an incline with friction, because friction is one of the main principal causes of damping. We have a ramp like this, and a spring like this. Let's say our ramp has a kinetic friction coefficient of, well, we can leave it undefined as mu k. And we have an object of mass m here with spring constant k that will happen to be displaced in this direction by a magnitude x1 or delta x, let's say. So what we can do is we can rotate our reference frame just like this in a very specific way. So you'll notice that right now gravity is acting on this object in a particular way right here. So now if I change my frame of reference, it's going to be acting this way. So all I've done is rotated my head. Nothing in the actual system has changed. So now what's going on here? We have definition of the x-coordinate, a y-coordinate, we have a theta, and of course this is going to be equal to theta 2. So how can we find the function of motion of this object? Well, let's see. What are the forces acting on it? The first force that we can see is, gravity. So you have, let's say we have some forces in the x direction, and we only care about the x direction because it's going to be confined to the ramp. The y direction doesn't matter. So Fx is equal to mx double dot. So of course the component of Fg that acts in that direction is going to be like this. It's going to be Fg sine theta. Now, of course, that's going to act in the positive x direction, as you can see here. Meanwhile, you have the restoring force of the spring. And what's that going to be? Well, the restoring force is always trying to pull it, well, in the opposite direction of where it is now, back to the position of equilibrium, which I'm going to call x equals 0. So this is minus kx, and of course the sign of x is going to change. So if it's right here, then minus kx will mean that it's pointing this way, while if it's here, minus kx will make it point this way. So then, finally, you have the force of friction. And the force of friction always acts in the opposite direction of this guy, right here. So I guess you could add a plus there.
I have a question. What is the necessity of rotating? If you don't rotate it, what happens?
If you don't rotate it, things become a lot harder to work with because
we cannot use mg.
It's
mg
not
sine theta, mg cosine theta.
You do know we're not dealing with a system that simple. It's going to be moving in this direction in a bunch of different ways, and that's a lot harder to describe if we don't rotate our reference frame than if we do. All we've done is turned our head. So Fg sine theta minus Kx plus, I guess you can say this. Now I'm going to be very careful with just putting that there, but something like this, for example.
Without proving?
It just tells you this is a unit vector, essentially. So, because if Fs is moving, hey, wait a second. Oh, no, never mind. This is dependent on the sign of the velocity. Doesn't really matter. So, we have the force of friction. So, for the first few seconds, the force of friction is going to be moving against the restoring force. So, that's what we're going to be using here. So, plus the force of friction, which is mu k Fn. And that's equal to mx double dot. Now, if you're familiar with the system at all, you'll already know you can break it up like this. And from here, you once again have a pretty simple situation. Why? Because the force of friction is always going to be constantly pulling. It always is just a constant. And technically, its sign is dependent on this. So this is what it gives us in the end. And of course, we can solve by just taking the constant solution, which is just and of course the non-constant solution, which is just going to be okay, so now we're just adding these two together. And you'll notice that at t equals 0, this has to be equal to delta x, which means that if we plug in t equals 0 right here, what do we get? This is not time dependent, so it doesn't really change. Now this is 0, which means we get plus a cosine phi. And the amplitude has to be, of course, delta x. So this has to be equal to delta x, which of course allows you to solve for the phase by just isolating cosine of phi. So now that is essentially how you find the full equations of this object being damped. I think it's a very interesting system. Thank you everybody for watching, and we'll see you in the next one.